Hello, everyone. Welcome back to Paglay Discount 2024. I'm thrilled to introduce our next speaker, Jasashvi Mishra. Jasashvi is a data engineer at AB InBev with an extensive experience at data modeling and data science. Jasashvi has been honored as a GSC scholar and received an Excellence Award from Samsung Research in India. Today, Jasashvi will be focused on a talk and we'll be discussing about beyond single models, the secret sauce of predictive success. Let's give a warm welcome to Jasashvi Mishra.
Hi, everyone. So, today, before getting started with my talk, I would like to share a small story of why I even thought of giving a talk on this particular topic. So, in the beginning of the year, I was working on a project wherein I found myself that even after using the best ML models, I was not getting the required accuracy. And this was a project on credit risk modeling to predict if a customer is worthy of being given a loan or not. And that's when I kept my research on and I stumbled upon the concept of ensemble learning. And that's exactly what I'm going to talk about today. Beyond single models, the secret sauce of predictive success. Here's a small intro about me. I am Yashasvi Mishra, currently working as a data engineer at AB InBev. I have been a part of a lot of open tech communities as I love being a part of, as I love technology. And apart from this, I am also very much interested and I love to contribute to numerous diversity and inclusion initiatives. That's why I'm part of communities like Pi Ladies, Women Who Code, Women in AI, etc. So, before getting started with the talk today, here's the agenda of what we are going to look at today. And so here's what we are going to see. First and foremost thing is that we will be going through the concept of wisdom of crowd, followed by understanding what exactly weak and strong learners are. Coming to the main topic of the day would be the ensemble learning and its different types. After that, we will be going into the detail of the different types of ensemble learning, bagging and boosting, stacking and voting, and we'll conclude today's talk by a comparison between in all of these techniques. So without any further ado, let's get started. Fun fact, a lot of scenarios in real life that happen are kind of the inspiration for ML concepts. So one concept is right in front of you, that is the wisdom of crowd. Now, what does wisdom of crowd say? It says that a single person tends to know very less as compared to a group of people. And that's exactly why, whenever we are holding elections to elect a leader of a country or a state, we tend to go for voting as a technique so that a single person might be biased to one individual candidate and can give a wrong decision. That's why we take the collective decision of people and decide upon the leader. Similarly, what happens in ML is that we leverage the collective intelligence of numerous machine learning models, and then we come to a reliable output or a collective prediction to kind of base our prediction upon. Coming to the topic of weak and strong learners. Now, weak learners tend to perform slightly better than random guessing. This happens because even after training on the training data completely, it tends to not capture the data pattern so well that whenever it is trained on a testing data, it tends to fail. On the other hand, strong learners tend to perform really well on the training as well as on the testing data because it captures the data patterns really well. So it is very, like, we can say that weak learners are having low bias and a high variance, whereas strong learners tend to have low bias as well as low variance. And just one example that we saw, right? Like the wisdom of crowd. We can very easily say that a single person is a weak learner, whereas multiple learners combining, like a crowd, is a strong learner. Now, I just talked about what exactly, about bias and variance, right? So let's just have a look of what bias and variance is. So you can see that I have a graph here of model complexity versus error rate. Now, you can see that when the model is complex, like when the model is not very complex, it is less complex, then the error rate is higher. This is because the same reason that we addressed, right? That it tends to capture less data patterns and hence it tends to fail on the testing data. So before like completely going into detail, I'll just tell you, like give you a small definition. So bias is error in training data and variance is error in testing data. So here, coming back to what I was explaining was that whenever the model complexity is less, it tends to capture less patterns in the data, and hence it leads to a higher error rate. Now, you must be thinking that when the model complexity increases, that is what we're seeing, then also the error rate is increasing, right? There needs to be a balance, right? Like in a lot of situations in real life, we tend to see that over of anything is not good. So, if a model is overly complex, it tends to capture the noise of the data, which can kind of, derail the prediction. It can distract the prediction. And that's why the error rate increases even if the model is overly complex. So there needs to be an optimal solution to this, right? So you can see that there's an optimal complexity that the model needs to achieve, because like on based on which it tends to capture the right features of the data and give us a reliable prediction. Coming to the main topic of today, ensemble learning. So, ensemble learning is nothing but combining multiple models and leveraging their collective intelligence to get a more reliable output. The pros of ensemble learning is that a better predictive performance, more robustness of the ML model, and less error rate. Let's just dive into the different types. So, we have four main types of ensemble learning techniques: bagging, wherein the same model, different versions of the same model train on different subsets of the data. Boosting, wherein is the model tends to correct its mistake by sequentially training on the data. Stacking, wherein models are stacked upon each other to give us a proper prediction. And voting, where different ML models tend to perform a majority voting and then decide upon one output. So, getting started with the first technique here, we have bagging. Now, as you can see, let's just clearly have a look at the picture, right? You see that we have original data and it is being bifurcated into different subsets. Now, one thing to note here is the different models that you see here, which are training on each of the subsets, is the same model. It's just that these are the different versions of that particular model. These are not different models, right? So, different versions of the same model are going to train on each of those subsets, give us a prediction, and then we are going to combine that prediction and get a final output. Now, this particular technique of dividing the data set into different subsets and training different versions of a model on it is known as bootstrapping. And when we finally get the output on out of each of these, we tend to aggregate those. And that's why bagging is very often also mentioned to be bootstrap aggregation. This is another name that we have. Now, in case of classifications, we aggregated using majority voting, but had it been regression, right? So, in regression, what happens is that there's a aggregation that is performed. We average it out. So, coming to now, what is happening here exactly? Okay. Now we remember, right, that bootstrapping happens. Okay, sorry. So, yeah, now bootstrapping happens, right, that we were talking about. Now, have you ever wondered on how bootstrapping takes place? How is the data bifurcated into different data sets? So, there are two techniques: row sampling and column sampling. You can see here that in the original data set, we tend to have 6 different columns with one target variable. Now, if we are going to take row sampling, we have two different subsets below. And in row sampling, what happens is any random 4 rows are taken of the data set and we bifurcate the data. In column sampling, what happens is any random 3 columns of it are taken and the data set is bifurcated. So the below subsets that are being formed, that are being created, are not just being created by only one technique, but both the techniques, row sampling as well as column sampling. So, there is one technique that we are going to come across very often, row sampling with and without replacement. Now, I'll just give a quick overview of what this means is row sampling with replacement means that the sampling, like if row number one is being used in the subset one, a replacement is being created for it in the backend. And when another subset is being created and it wants to use row number one, it can use it. However, if it was without sampling, if the row number one is being used in the first subset, it is not allowed to be used in any other subset going forward. So that's exactly what with and without replacement of row sampling is. Here's a small GIF showcasing the bagging technique. We can see that the data is getting bifurcated and then it is being fed into different ML models and different versions of the same ML model and giving us an aggregation. Now, here is one the code samples that I've attached for your reference. It also has 4 different types: bagging, wherein the row sampling is being done with replacement; pasting, where the row sampling is being done without replacement; random subspaces, wherein the bifurcation of the data set is using column sampling; and random patches, wherein the subsets are being created using row sampling as well as column sampling. Coming to the second technique, that is boosting. Now, boosting, as we all know, that uses the sequential technique to correct its mistake in the past and give us a proper prediction. Now, just having a look at the picture right in front of us, what is happening is we have an original data set and we have an ML model training on it. That gives a prediction. On some data points, it corrects rightly. However, on other data points, it tend to give a wrong prediction. Now, in the next sequence, what would happen would be that the areas where it has performed in a wrong manner are going to be weighted more, so that when the next time the ML model trains on the same data set, it is going to focus more on those data points and then give us one more prediction. And then it is going to, at least on some of the data points, it is going to give us a right prediction, right? So, in that manner, what happens is like this particular cycle continues for the number of uh, for the number of frequency we are going to define in the ML model, and in a sequential manner it is going to correct its mistake and then give us one final prediction. So here's one small illustration of the same. Let me just play this. So the data is like sequentially being trained, and then there's a feedback, and on feedback it is correcting its mistake and then giving us a final result. Okay. So here's one example for the same XGBoost classifier. Here the n estimators are put to 1800 times it's going to perform this particular cycle and give me a correct prediction. Okay, it is going to correct its mistake and then give me a proper prediction. And I got like the accuracy to be more like a very realistic one, around 88%. Coming to stacking ensembles. Now, in stacking ensembles, what happens is, again, let's jump right into the picture and understand. You can see that we have a training set, okay? Now, model 1, 2, and 3, each one of them is being trained on that training data set. And with the predictions on out of each of these models, a new training set is being formed. Now, a new training set is being formed. So, there's one meta model that is going to train on this particular new training set and then give us a final prediction. To understand this better, you can see that the predictions from model 1, 2, and 3 is P1, P2, and P3. So the new training data set that we have is P1, P2, and P3 with one target variable. And the testing set is the same. And one meta ML model is going to train on this new training set and give us a output. So technically, meta model is stacked upon these 3 ML models. So here's again one code sample for you. We have random forest and decision tree classifiers as the initial level of models. And we have the meta model as logistic regression, which is stacked upon these two. It kind of performs a class it performs, it gives us a prediction based on the predictions on the previous models, right? And we get an accuracy of around 87%. Coming to voting ensembles. Now, voting ensembles, you must be thinking, right, that it is very similar to bagging. Why are we even using it? So, in bagging, you would remember that we were saying that in different subsets, it is the same model that is being used. It's just that the different versions of the same model, right? In voting, what happens is you can use different models. And after that, you can work, like basically do a majority voting on each of those outputs and get a final prediction. So as we can see here, model 1, 2, and 3 give output as 1, 0, and 1 respectively. After a majority voting, we decide upon the output to be 1. Here's a small illustration of the same, that whenever an MRI scan happens, Doctor 1, Doctor 2, and Doctor 3 give their inputs, right? No tumor, tumor, and no tumor. So, what happens is that similarly in ensemble learning, what is happening is that MRI scan is going to give the same output, and we have a maximum vote to no tumor, and hence there is no tumor. So, just this was the illustration. Let's head on to, yeah, the code sample. You can see here that we have three different ML models: logistic regression, random forest classifier, and decision tree classifiers. And each of them is going to give an output upon which we are going to have a voting classifier, and we are going to get the output after the majority voting. Had this been the case of regression, what would be happening here would be that my voting parameter would have been defined as soft, and a aggregation would have been done on those outputs. There wouldn't have been majority voting in that case. So here's one comparison between all of the techniques that we just discussed: bagging, boosting, stacking, and voting. In bagging, in bagging we have like the same model, and our primary focus is on reducing the variance. However, in boosting, it is the same model, but we are sequentially correcting the mistakes. And in stacking, it is primarily focused on using a number of ML models to have a better prediction. Same is the case for voting. It is also focused on using different models to get a proper prediction. And bagging is like there's an independent training of the ML model. However, in boosting, what happens is that it is a sequential training, right? Yeah, like we just discussed. In stacking also, it is parallel, and same in voting as well. So the strength, let's just have a look at their strength. Bagging reduces the overfitting. Boosting, it improves the accuracy very much, and it handles different difficult cases. Stacking, combining the strengths of the different models, same as voting. So yeah, this was our comparison. Coming back to my initial story, right? Like how my prediction was not what I was expecting. So it was around 64%, as you can see right here. And when I used ensemble learning, I used XGB classifier, and I got an accuracy of around 88%. So this was very much realistic, and this was the accuracy that I was expecting. And thankfully, ensemble learning came to my rescue, and here the prediction is. So thank you so much for, giving me a chance to give a talk here. And you can get in contact with me on LinkedIn, Twitter. And here's a link to the notebook wherein I have performed all these techniques, and you can have a look at the same. Thank you again.
Hey, Yasashri, it was a great talk. Thank you so much for being here, explaining all your expertise at IDETISCON 2024. I hope so everyone enjoyed the talk, and then just let's continue with the program at the conference.